We're now going to derive the current gain in a simple transistor circuit. That's the equation 2016 in your textbook. The first thing that we have to do is we have to take this circuit and convert it to an AC equivalent. And that will look something like this. Remember, in the AC equivalent circuit, all the capacitors become shorted. So we can kind of sort of do that. They become short-circuited. And the power supply, VCC, also becomes short-circuited. So there's like a connection goes from here directly to here. So the AC equivalent circuit, then, redrawing it with these new lines in it, simply has R1 in parallel with R2 because they're connected together at this point, and that end of R1 is connected to this end of R2, so R1 and R2 are definitely in parallel. And then comes a transistor which has a Z to the base. And notice that there's no AC resistor here because this emitter resistor is completely bypassed by the capacitor. We have the collector resistor, RC, and here we have the load resistor RL coming from the collector again in parallel with RC. So this is the equivalent circuit for AC equivalent circuit. Now what we like to do is that we like to find the relationship between I in of the circuit, and I in is here, and I out is here in the load. First thing we notice that the input current is going to be divided. Some will go through R1, some through R2, some into the impedance in the base. And so we have to find out how much current goes into the base, I base. To do that, we're going to use the current divider rule. So we're going to write an expression to define the input impedance of the whole circuit, Zin. Zin is equal to R1 in parallel with R2 in parallel with Z in the base. Now, you remember what the base impedance of a transistor circuit is? Z into the base is equal to beta times Re prime plus R capital E. That's to say an AC resistor in this path. In our case, the resistor is completely bypassed, so this term here goes to 0. And all we're left with is beta Re prime. This beta, of course, is HFE. Re prime, you'll recall, Re prime is equal to 25 millivolts divided by the DC current in the emitter. So to find the DC current, we have to first find the base voltage, then the emitter voltage, then divide that by the emitter resistor, plug that into here, and that will give us Re prime. So the question now is, what is the relationship between I in and IB? Well, we're going to apply the current divider rule. IB is equal to I in times Z in divided by Z in the base. Now remember, the current divider rule simply states that the fraction of current that goes into any path is the total impedance divided by the impedance of the path that you're interested in. So here it is. Now we're not really interested in the base current, we're actually interested in I in. So I in is equal to, let me just flip this over, is equal to the base current times the base impedance divided by Z in. So there's an expression for input current. Now we'd like to find one for the output current. And again, we can apply the current divider rule. And here it is, simply that
it's 4 o'clock.
I out is equal to IC collector current times the RC over RC plus RL. And now that we have this, we can substitute IC for another expression which relates it to IB. And recall that IC is equal to beta or HFE. In our case, we're dealing with the AC signal. HFE, small fe, times IB. And so we're going to make that substitution into here. So I out is actually equal to HFE IB times RC over RC plus RL. Now, this tells us that the current gain is equal to, now we're just going to take the ratios, I out divided by I in. So we have HFE IB times RC over RC plus RL divided by IB over Z base over Z in. Now right off the bat you can see that the IB's cancel out. And of course we can flip this over and bring this up to the numerator. So what we end up now is HFE times RC divided by RC plus RL times Z in divided by Z base. And here is the expression for current gain, AC current gain. Now this looks a little bit different than that found in the textbook. The author states, the author has an equation which says AI is equal to HFE times Z in over Z base times RC over RL. Now this RC, small c over here, is in fact the AC resistance that the collector sees. So remember that RC is equal to RC times RL, the product, over the sum. And we can show that this equation and this equation are essentially the same by noticing that if we were to bring RL over to this side of the equation, we would have RC divided by RL is equal to RC. This is the AC resistance of the combined one. This is just the collector resistor. RC plus RL. And notice that the author has chosen here to use this side of the expression, and the one that we ended up deriving up over here just happens to be this side of the equation. So in fact, these two equations are exactly the same.